important. Okay, so let's start off with electron pudding. All right. Now, you guys all know the basic argument, right? The electron argument for why there should be plum pudding. This is Thomson's argument. Remember this? We start off with, we know that electrons are negatively charged, right? What else do we know about electrons? We know that they are what? They're smaller than, they're tiny, they're smaller than atoms. Are smaller than atoms. Smaller than atoms. Writing quick. And we also know what? We know that, what else? That atoms are neutral, generally. Are neutral.
Those are the 3 rules.
Those are the 3 rules. Then, from this, we can come up that, this therefore,
Protons are
it's a predator symbol. Therefore, we know that electrons must be inside atoms. Are inside atoms. And atoms, Gesundheit, must have some positive stuff to balance out these electrons. Positive stuff. Okay, this is Thomson's argument right here. This whole thing, Thomson. J.J. Thomson. Thomson's argument. And his argument made him think, okay, well, since we have this positive stuff right here and we have these negative electrons, maybe the model of the atom looks something like this, where we have, overall, we've got this kind of positively charged, this is the positive stuff, positively charged stuff. This whole area, this whole region is positively charged, but then embedded in that positive charge, perhaps, said, we have these little negative electrons. And this whole model right here looks like plum pudding. So that's a plum pudding model. So that's the first part. That's the first thing what we learned. And we even saw little electrons going across in the cathode ray tube. Remember that? Good. But this got disregarded. This model of the atom got disregarded because we had Rutherford come along and he did something. He shot those alpha particles. He shot them at a gold foil, and to his surprise, they did not go right through this. They should have, according to the plum pudding model, but they didn't. What happened?
Are we gonna have to know if like whose argument it was?
Yeah, Rutherford's a guy who.
But are we gonna have to like say that on the test?
They'll be in the form of like multiple choice questions or true false, but they're tough true false and tough multiple choice, so you have to know who did what. This is J.J. Thomson. There's 3 guys you need to know, 3 scientists you need to know. That's J.J. Thomson, Rutherford, and Bohr. Okay. J.J. Thomson was the guy who discovered the electrons, and he came up with this argument for the plum pudding. Rutherford was the guy who shot those particles at gold foil, and they bounced back, to his surprise. Because they bounced back, that must mean that there's something positive and very massive in the middle. We said that they're in the middle.
Means a nucleus.
And he said, oh, it's not all spread out, this positive charge, it's not all spread out. Instead, I think this positive stuff is concentrated. It's compacted. You see those trash compactors? Anybody ever see those things? You know what I'm talking about? Or maybe just even like the trash cars, trash vans, whatever they call them. Dump trucks. They compact all the trash together. They squish it together into this really condensed little area. So that right there is a condensed little area. And this, Rutherford called the nucleus. And inside the nucleus was protons and neutrons. The protons were positive, the neutrons were neutral. Both of them were very massive. And according to Rutherford, these electrons, he said, well, they probably go around the middle nucleus like stars around, or like planets around a star. So he called that the planetary model.
The nucleus is protons and neutrons?
That's right.
What was the experiment that Rutherford did?
He threw it against gold foil.
It's the gold foil experiment. That's what it's called.
So what did he throw at?
He shot, well, throw, like in quotes. He shot these alpha particles, which are positive particles, at the gold foil. And some of them bounced back. Not all of them bounced back, but some of them did. Which made him think there must be something very massive in the middle there to deflect those. You okay? Good? All right, good. All right, so that's the Rutherford model. That's the planetary model. We got those two done. We got the neutrons and atoms. That's done so far. Wow, that's pretty good. But now we go into a little bit more technical detail and talk about masses of these atoms.
Can
So
you
let's
see
say-
that board from the screen?
Excuse me?
Can you see that board from the screen?
Yeah?
Board on your right.
No, you can't.
Oh.
Let's see. So, where are we at right now?
Wait,
I just get distracted.
Who did the experiment prove that there was positive?
That there's something very dense and positive and massive in an atom. And so he called it the nucleus. Now, this sound's picking up, I hope. Yeah, it is. I gotta talk a little bit louder, because the sound doesn't pick up all that great. Bring it closer. Oh,
The camera.
camera's fine. It's still attached. It's okay.
Hello, camera.
You guys could, if you want to watch it right here, you could. Oh my God!
Just undo, yeah.
Oh, it's fine. It's fine.
So unplug it and replug it.
That's what we're seeing right now. Okay? Is everybody? All right. We're steady.
Is it working? Is it
You want to point it more towards. Yeah, keep on going, keep on going. Keep up. Oh, go the other way. That way. Wait, stop. That way.
Stop.
Stop. Oh my God.
There. Perfect.
Chloe,
Right
you're perfect.
there. Perfect. That's it. All right then. We were talking about this. All right. So now let's say that you've got. We're going to talk about any element, any old element, and these are the kinds of questions I ask you. I say, okay, well, you've got the overall atomic mass is something like 32, and the amount of protons is. What should I make the protons? I'm going to make the protons be 16. No, it's not. Oh, yeah, it's okay. How many neutrons do we have now? And how many electrons do we have if the charge of this atom, the overall charge, I'm going to say the charge now is plus 2. Whoa, we got lots of stuff we can fill in right now. Isn't that cool?
You
We can
added some.
deduce. I know you love deducing. How many neutrons do we have right now?
16.
We gotta have 16. So this is the type of question I ask you on this test. How many electrons must we have?
30.
Try again.
Oh, 34.
No, 14.
How many positives do we
14,
have?
14.
We have 16, so it has to be 14 because the charge is determined by the amount of protons and the amount of electrons. These are the negatives, these are the positives. So since we have 16 positive and 14 negatives, the overall charge is 2.
charge. That makes sense.
Makes total sense.
Let's cross that one off.
All right, good.
Is that isotopes
Now-
and hydrogen?
No, that's neutrons and atoms. That's just going in a little bit more detail. Right. So now let's talk about isotopes and average atomic mass. So let's say we've got, let's say that we have one atom, let's say it's carbon, and this carbon has 6 protons, right? And how many neutrons does it have, if you see that little 12 up top?
6.
6, that's right. So this one has 6 protons, 6 neutrons. But we can also have this carbon that looks like this. Woohoo! How many neutrons does it have now?
8.
It has 8. What do we call these two things? Yes, they're like brothers. They're isotopes.
They're related.
What are isotopes?
These two are different versions of carbon. So we call that isotope. So we want to figure out now, let's say I go throughout the whole universe and I find that, let's see, 98.2% of all carbon is this kind of carbon. And what would the remaining be? 1.8% of all the remaining carbon is this carbon. And I want to know what the average atomic mass of carbon is. Ooh. What's the average atomic mass? The better question is, how do we find it?
Do 12
You do 12.
times.
Okay. 12 is, why are you getting 12? Where are you getting
That's
that
the
from?
atomic mass.
That's
Not
right.
that isotope.
So 12.
Times 98
Point
or
two.
0.982.
Good. Why did you change it to 0.982?
Make it decimal.
Right, you're changing this percentage right here into a decimal.
Added by 14 times 0.01.
Yes, and that's the trickiest part. That's where you're going to lose points on the test, is because when you turn this into a decimal, it's not just 0.18, it's 0.018.
Why? Oh, it has to be 2 decimal points.
Right, because you, like you say always, you say, oh, to change it into a decimal form, you have to divide it by 100, right?
Yeah.
Yeah. So that's it. Okay, so if you do this operation, 12 times this plus 14 times that, you get an average atomic mass. And you can figure that out. Good. You got it, Max?
12.036.
12.036. And it's always going to be an AMU. The units. Don't forget your units. That's an easy way to lose points. And you don't want to lose easy points. Come on.
The thing that I didn't understand yesterday was how to do the inverse, like the
Well,
opposite.
that's later on.
Ooh, we're later on the inverse.
Not the inverse, like when you do, you have to find the opposite. Like if
You want
somebody
me to
already gives you the atomic mass and you have to find the percentages.
The average atomic mass, and you want to find the percentages. Okay, we can talk about that real quick. I hope this isn't confusing. This is the harder part of this type of question. This is an easier type of question for average atomic mass. Okay, a harder one would be something like this. If I say the average atomic mass of carbon is, let's say that it's 12.01, and I don't know what these percentages are. Okay. Let's say I don't know what these things are. How would I find the percentages now? If I give you the average atomic mass, and I want to know now the percentages. I want to know what these things are. What's this, and what's this? Okay.
That 12.
How would you set this up, Chloe?
I have no idea.
All right, I'll give you a hint. We can put X for one of these. Let's put X for this one. Doesn't matter which one we start off with. Okay. And then the other one, you can say this one is 1 minus X. Same X. So I'm going to make this the same color. 1 minus X. And this whole thing equals 12.011. Because that's the average atomic mass. Is this going to ring in some bells, maybe? Maybe not?
It's a ringing.
This is the hardest type of problem I can ask you for this. Average atomic mass. Baby. So this is the hardest type. So how would you now solve for X?
You multiply.
Multiply it out. Yeah, let's distribute those X's. So 12X plus, and that'd be 14 minus 14X equals 12.011. Now let's combine like terms. How about that?
So it's 14 minus 2x.
Oh, without.
12 minus 14.
You mean 14 minus 2X?
No, it's negative 2x plus 14.
Yeah, because you're combining these two terms, right?
That's still 14 minus 2x.
So this is going to be, no, it's not.
No, it's not. It's 14.
Negative 2x plus 14.